Welcome to this lecture on the fundamental theorem of duality. If you have ever wondered how businesses guarantee they are making the absolute best financial decisions, you are in the right place. Today, we are going to explore a beautiful mathematical concept that proves every optimization problem has a hidden mirror image. By the end of this video, you will understand how these two perspectives perfectly align. Now that we know what we are studying, let us understand why this concept matters. Imagine you own a bakery. Your primary goal is to maximize your profit using a limited supply of flour and sugar. This original goal is what we call the primal problem. Now imagine a competitor wants to buy all your raw ingredients instead of letting you bake. They want to spend as little money as possible, which forms their dual problem. To convince you to sell, they must offer prices that guarantee you make at least as much money as you would by baking. These two completely different perspectives are mathematically linked. Before we can connect the primal and dual problems, we need to define them mathematically. Let us start with the standard primal problem. Conceptually, this represents our goal to maximize total profit. We define this profit as Z, which equals C transpose times X. Here, C represents the profit each individual item makes, and X represents the quantity of each item we decide to produce. This maximization is subject to constraints, written as matrix A times X is less than or equal to vector B. Matrix A is the resources needed, and B is the maximum resources available. If we increase our available resources in vector B, our maximum possible profit Z can also increase. Now that we have our primal problem, let us look at its mirror image. The dual problem flips our perspective. Instead of maximizing profit, the competitor wants to minimize their total cost, which we call W. This cost equals B transpose times Y. The vector B comes directly from our primal resource limits, and Y represents the dual variables. These dual variables are incredibly important. They represent the shadow price, or the hidden monetary value of each unit of resource. The minimization is subject to the constraint that A transpose times Y must be greater than or equal to C. This ensures the competitor pays at least the profit value of the products. With both problems defined, we can introduce the mathematical relationship between them. First, we have weak duality. Conceptually, this means the profit you make can never exceed the total valuation of your resources. The formula shows that any feasible profit is less than or equal to any feasible cost. But the fundamental theorem of duality, also known as strong duality, takes this a massive step further. It states that at the optimal points, which we call X star and Y star, the gap between these two values completely disappears. The maximum possible profit exactly equals the minimum possible cost. If the optimal profit increases, the optimal cost must increase by the exact same amount. Before we prove why this theorem works, let us see it in action with a concrete example. We are given a primal problem where we want to maximize Z equals 3x1 plus 5x2, subject to three resource constraints. We are also given the optimal solution, x1 equals 2 and x2 equals 6. Our goal is to verify that the primal and dual optimal values are identical. First, we calculate the optimal profit by substituting our given x values into the primal objective function. 3 times 2 is 6 and 5 times 6 is 30. Adding these together gives us a maximum primal profit of 36 units. Continuing with our example, we now need to construct the dual problem to see if it matches our primal profit. We create the dual objective function by taking the right-hand side resource limits from our primal constraints. Those limits were 4, 12, and 18. Therefore, our dual goal is to minimize W, which equals 4y1 plus 12y2 plus 18y3. We are provided with the optimal dual solution. y1 is 0, y2 is 1.5, and y3 is 1. Notice that y1 is 0, meaning the first resource is not fully used up and has no shadow price. Now we will calculate the final dual cost. We substitute our optimal dual values into the dual objective function we just built. 4 times 0 is 0, 12 times 1.5 is 18, and 18 times 1 is 18. Adding these together, we get a minimum dual cost of 36. This perfectly matches our maximum primal profit of 36. We have successfully verified the fundamental theorem of duality. The physical meaning here is profound. The maximum money you can make from production is exactly equal to the minimum valuation of the resources you used. Now that we have seen the theorem work in practice, let us understand where it comes from by proving it. We will start by establishing weak duality. This chunk of the proof sets up the relationship between the constraints. We begin with our primal resource constraint, matrix A times X is less than or equal to vector B. We multiply both sides by the transpose of our dual variables Y. This gives us our first key inequality. Next, we take our dual constraint, A transpose times Y is greater than or equal to C, and multiply both sides by the transpose of our primal variables X. This sets the stage for us to combine the two perspectives. Continuing our derivation, we look at the result of multiplying the dual constraint. We get X transpose times A transpose times Y is greater than or equal to X transpose times C. Here is the mathematical trick. These are just scalar values. The term X transpose times A transpose times Y is exactly the same number as Y transpose times A times X. Similarly, X transpose times C is identical to C transpose times X. Because these middle terms are the same, we can link our two separate inequalities into one continuous chain. This proves weak duality. The primal profit is always less than or equal to the dual cost. This brings us to the final conclusion of our proof. We just established that for any valid production plan, profit is less than or equal to cost. But what happens at the absolute best, optimal points? When we use the simplex method to solve the primal problem, the algorithm searches for the highest possible profit. When it finds the optimal primal solution, X star, a beautiful thing happens. The final row of the simplex tableau automatically generates the optimal dual solution, Y star. Because of how the algorithm terminates, the objective values are mathematically forced to be identical. This gives us our final result. Maximum profit exactly equals minimum cost. Let us visualize everything we have just proven. On screen, you are looking at a vertical axis representing the objective value, either profit or cost. The upward arrow represents the primal problem. It is trying to push the value up as high as possible to maximize profit. The downward arrow represents the dual problem, pushing the value down as low as possible to minimize cost. Because of weak duality, the primal arrow can never cross above the dual arrow. They are trapped. Ultimately, they collide exactly at that red dot in the middle. That intersection is the optimal solution, where Z star equals W star, visually proving that the gap between them completely disappears. Now that we understand what happens when a perfect solution exists, we must ask, what happens when things break? Not every problem has a neat, finite answer. Sometimes a primal problem is unbounded, meaning its profit can grow to infinity without breaking any resource constraints. The fundamental theorem of duality gives us a strict rule for this scenario. If one problem is unbounded, its mirror image must be infeasible. Infeasible means the mathematical constraints contradict each other, making it impossible to find any valid solution at all. Let us look at an example to see exactly how this contradiction happens. We are given a new primal problem where we want to maximize z equals 2x1 plus x2. This is subject to two constraints. The first is x1 minus x2 is less than or equal to 10 The second is 2x1 is less than or equal to 40. As always, our variables must be non-negative. We are going to analyze this primal problem to see why its profit can grow infinitely large. Then, we will build its dual problem to prove that it has no valid solution. Let us look closely at the first constraint. If we keep x1 fixed at 0, the constraint simplifies to negative x2 is less than or equal to 10. Because x2 must be a positive number, making it negative means it will always be less than 10, no matter how large x2 gets. Since there is no other constraint limiting x2, we can increase it to infinity. Because x2 has a positive coefficient in our objective function, our total profit z also becomes infinitely large. The primal problem is officially unbounded. Since our primal is unbounded, the theorem tells us the dual must be infeasible. Let us prove it. We formulate the dual constraints by reading down the columns of the primal problem. The primal objective coefficients, 2 and 1, become the right-hand sides of our dual constraints. Reading down the x1 column gives us our first dual constraint. y1 plus 2y2 is greater than or equal to 2. Reading down the x2 column gives us our second dual constraint. Negative y1 is greater than or equal to 1. We need to analyze the second constraint. Let us solve that second dual constraint. We have negative y1 is greater than or equal to 1. If we multiply both sides by negative 1, we must flip the inequality sign. This leaves us with y1 is less than or equal to negative 1. However, a fundamental rule of all linear programming is that variables must be non-negative, meaning y1 must be greater than or equal to 0. It is mathematically impossible for a number to be less than negative 1 and greater than 0 at the same time. This contradiction means the dual problem is completely infeasible. So, why do we care about this theorem outside of a math classroom? The fundamental theorem of duality is the backbone of modern operations research. In real-world supply chains, the dual variables allow managers to calculate shadow prices. A shadow price tells a factory exactly how much extra profit they would make if they acquired one more hour of labor or one more ton of steel. Furthermore, if a massive logistics company has a scheduling problem with millions of variables, the primal problem might crash their computers. By using this theorem, they can solve the much smaller dual problem and guarantee they found the exact optimal profit. We have covered a lot of ground today, so let us review the key takeaways. First, every linear programming problem has a shadow problem, and they are intimately connected. Second, weak duality acts as a boundary, ensuring that profit can never exceed the valuation of resources. Third, the fundamental theorem, or strong duality, guarantees that when solved perfectly, the maximum profit equals the minimum resource cost, leaving zero gap between them. Finally, if one problem spirals to infinity, the other breaks down completely. You now have a deep understanding of how duality provides a built-in economic interpretation for optimization.